Good morning. Again, we start on page 9 today. Our quick look at the calendar. Last class, the plan for project number 2 was due. I got a lot of plans, but I didn't get all the plans. So if you have not turned in a plan yet, ASAP. Today we talk about population growth, so this is more kind of math as it relates to nature. And then again, we've just got a few more days of new stuff to do, 5 classes, including today, of new material, and then our review day for the test. Any questions about the calendar? Okay, so then we're here on page 9, and we'll start up here with number 1. Maggie? Okay, thank you. So we've got lots of different uses for the word population. Usually it describes like animals or people or something like that, but population could be money. It could be anything that is growing. And so we're going to talk about how things might grow today. We'll go to Zach K for number 2. Okay, so we've got some notation here that I'm hoping reminds us of some stuff we did last time. You guys remember the F1 and the F2 and the F3? This is the list of numbers for the B problem. Remember we ended up coming up with how many B's there were. In the first generation was just the single male B. In the second generation, that B had a single mom. And then in the third generation, the mom had 2 parents. And then what's the fourth number here? It's 3. It turned out add the previous 2. So we had this list of numbers. It's called the sequence, just a list of numbers. And today we're going to talk about other lists of numbers. So for example, we could talk about the population here in Greenfield on January 1st of every day for the last 20 years. So let's just say maybe 20 years ago on January 1st, I'll say the population of Greenfield was, I don't know, 8,000. And then P1 is supposed to represent the population 1 year later. Okay, maybe we were at 10,000. And then P2 is the population 2 years later. Maybe we go back down. It doesn't have to keep growing, right? Could go up, could go down. The right-hand side is the possible populations of Greenfield. Left-hand side is just naming it. And the numbers are supposed to tell you when we are looking. At what moment in time am I telling you about? Year 0, year 1, year 2, year 3, okay? So it's just numbering the list of populations, just like we numbered the bees up above, okay? All right, let's go to 3. Holly. Okay, so there are a couple of different, all right, so populations are quite complicated. Could go up by, what happened in the first year? What did the population do? Went up by 2,000. What happened in the second year? Went down by 1. Like, we look for patterns, and populations are quite complicated. We're going to simplify some things, and we're going to look at a few possible ways for populations to grow that we can kind of get our hands on. Easy patterns, easier than this, which there's no pattern at the moment that I can see. So suppose that instead of saying it went up by 2 and then down by 1, suppose that I say it just keeps going up by 2 every year. Then how much do we have in this year? We have 12,000, and then in year 3, 14,000, and I can get my hands on that pattern. I can talk about that pattern if I assume it just keeps growing by 2 every year. Now that's a big assumption. It's probably not valid for Greenfield, but for some things, I think it's a good assumption. So, so let's talk about that particular kind of thing. This kind of growth where it's up by the same amount every year, like up 2 every year, is called linear. It's a linear growth model. And we'll go to number 4 for Alex. Or we'll go to Jocelyn while Alex finds this. Page 9, number 4. Okay, so let's take a look at this. These made up numbers up here. What is the starting population for Greenfield? 8,000. So I'm telling you that we start with 8,000 people. And then I'm going to tell you that we grow by 2,000 every year. And if you know those two pieces of information, couldn't you predict what the population will be at any moment in time? Like, that's all that you need. You need to know what we start with and how much we gain every year. And you have everything you need to know if you have those two pieces of information. So that's what Jocelyn just read to us there. Yeah, I think that's good. Let's go to 5. Blake. Okay, so let's try this one. First thing I want to know is P0, the population, the amount of stuff in the tank at the start of this experiment. It's 35. Okay, we start with 35. And then it says every year the reactor generates 5 tons. Every year you gain 5 tons, just like every year we gain 2 people, right? So this is called linear. Every year you gain the same amount. So we're going to write this in 2 different ways. First one we're going to write is this thing called the recursive formula. And we saw this word last class, and I'll remind you that we had a recursive formula for the Fibonacci sequence. We said if you want to figure out the current Fibonacci number, you take the Fibonacci number from one generation earlier, and then you add the Fibonacci number from when? From 2 generations earlier. We wrote that formula in class the other day. So that just said to get the current Fibonacci number, you have to add the 2 previous Fibonacci numbers. And that's called the recursive formula or recursive rule because you keep using it over and over again to generate the list of numbers. Yeah. Yeah, so this number right here is how many bees in the previous generation, and then this number here was how many bees in the generation before that one. And we just added the 2 previous numbers to get the current number. But it's a different rule here for this nuclear waste stuff. It says that every year we gain 5. So let's think about this. If I gain 5 every year, then to figure out what I have this year, what I'm going to do is I'm going to take what I had last year and do something to it. How do you figure out how many tons of waste you have this year if you know what you had last year? We add 5. That's it. That right there is the recursive rule. In English, it says you take how much stuff you had last year, 1 year ago, that's the n minus 1, and you add 5, and that will tell you how much you have today. And if I wanted to, I could be real explicit here and just list a few things. How much stuff is in the tank 1 year from the start? It's 40. And then 2 years from the start, 45. What are you doing every year to get the next year? You're just adding 5, right? Whatever you have at one moment in time, you add 5. That's next year. So that's all that we've done here. This is the math, very general way to write. Take what you had last year and add 5. Questions on that? Yeah. Yeah, so you could, yeah, you could use this. These 2 things here are what we call the recursive formulas, and you could use it to find out what's happening in 10 years. But there's a weakness. What do you need to know to figure out how much stuff is in the tank in 10 years? You need to know what was happening at 9 years, because then I can just add 5. But how do you figure out what's happening at 9 years? What do you need to know? You need to know what was happening in 8 years. So it's kind of annoying because you can't get information about year 10 without having the previous 9 all the way figured out.
Yeah,
without,
when you're working with a known transition, it's going to increase 5 every year. is it really necessary to do that? Because if you want to know in 10 years, you just take your 5, multiply that by 10, and add it to your initial 5.
How's that feel? If we want to look 10 years down the road, we know we're going to gain 5 10 times. So maybe we're just going to gain 50 plus what we started with. Yeah, and so Jason is predicting what we're going to call the explicit formulas. And they're way better if you can get them than the recursive formulas, because the recursive formulas involve knowing what happened the previous 9 years before we can finally talk about year 10. So let's, yeah.
Recursive formula is all like as a part of the linear growth.
Yes, this is a recursive formula for a linear growth model. Yeah, but recursive is more general. Here was a recursive formula. It wasn't linear, the Fibonacci list, but that's a recursive formula just because it refers to previous generations. Yeah. Okay, so we've got symbols here. I just want to show you real quick. You don't need to go here just yet, but on the next page, there is a formula given out for the linear growth model. And it just says this. It says if you want to know what Pn is, you take Pn minus 1 and you add the common difference. What did we gain every year with the nuclear waste thing? We gained 5. So that's the formula. It's always Pn equals Pn minus 1 plus whatever the common thing is, plus 5 in this case. Okay, well, let's see if we can figure out what, Wadada, were you going to say something similar? Okay. So let's see if we can write down something more along the lines of what Jason and Wadada are thinking. I want some explicit formulas. So we're going to write these over here. So let's see if we can kind of write down an equation that gets at what Jason was saying. If you want to know how much stuff you have n years into this experiment, 5 times n plus 35. What was that, Zach? Yeah, Zach says 5n plus 35. Jason? Yeah, so we'll have a general thing in a second. Yeah. What do we think? You started with 35. You just have to figure out how many 5s you're going to add. How many 5s you're going to add? N 5s. However many years into this process we're thinking about. And just to kind of verify that, what if we tried plugging in, for example, to find P3 from that equation that's in black? According to this equation, instead of n, what are we putting? Putting 3. So this becomes 5 times 3 plus 35. 15 plus 35 is 50. Was that what P3 was doing it the long way? Yeah, P3 is 50. If you had a choice, would you prefer using the recursive or the explicit? Explicit. The explicit allows us to answer Alex's question like that, right? He wanted to know what's happening in 10 years. Okay, you could use the red formula 10 times in a row, build your way up to 10 years into the future, or you could use this black formula once. What are we plugging in for n? If we want to know what's happening 10 years down the road, we plug in 10 for n. What do we get when we plug in 10 for n? P10 equals 5 times 10 plus 35. Answer to Alex's question is there were 85 tons in the tank 10 years down the road. Whole lot better than using the red thing over and over again. Okay, this is fine. Let's answer this follow-up question. It says, how long will it take for the tank to fill up? Okay, so we want, what do we want? How much stuff will fit in the tank altogether? It's 100. That's the capacity here. Yeah, and we're actually going to do that by solving an equation, but intuitively Johannes is saying he feels what we should be doing. But we know we want 100 things in the tank at some moment in time. So right there, 5n plus 35. That's how much stuff you have in the tank at any moment in time, at some general moment in time. And what do I want it to equal when the tank is full? I want it to equal 100. So we solve an equation. And how do we solve that equation? Yeah, we do what Johannes had said. First you subtract 35. And then there's algebra. Who knew? And then we divide by 5. So it will take 13 years for this tank to fill up. Questions on that? Okay, let's go to Sam. Can you read this, the 5 part here? Okay, and you guys see that, right? What do you get when you subtract 50 minus 45? 45 minus 40? 5. So every difference is 5, so we call it the common difference. And then on the next page, it allows us to use that formula right there. And in fact, the formula that Jason wanted to think about, I think, is this guy. Let's just make sure that we get the same thing that we got before. Pn equals, what's the start amount? It's 35. That's how much stuff we started with. Plus n times, what was the common difference? 5. Is that the formula that Zach gave us? Yeah, it's rearranged, but that's equivalent. Zach, what did you say? 5n plus 35? Same thing. Okay? So if you feel why it was 5n plus 35, then super. You don't need the formulas. But if you want formulas, you got them. Write them on your reference sheet for that last test. Okay? All right. We are going to skip number 6 and jump down to number 8. Alex. Keep going. Okay, so let's think about this. Instead of adding 5 tons of waste every year, imagine that the number of tons of waste multiplied by some amount every year. Okay, so that probably doesn't make sense for the waste, but for example, maybe you have money in a bank account, and because of the interest that it gains, like every year the money doubles, something like that. So like if you don't have very much money, then double it, it's still not all that much. But if you have a lot, then doubling could mean something significant, right? So here's the question. Last night, my uncle called me. He lives in New Hampshire, and he called me because he had just read some little magazine, AARP, for the, what is it, Association for the, what is it? It's a true story. My uncle called me last night. And anyway, he was reading in some magazine about this problem. It said, if you were to retire, would you rather have $100,000 given to you right now in one check, or a penny today, 2 pennies tomorrow, 4 pennies the next day, 8 pennies the day after that, doubling for 1 month, 30 days? That's the question. So you can either have $100,000 right now in one lump sum, or every day for the next month, we're going to give you a penny, and then 2 pennies tomorrow, and then 4, and then 8. But we start with only pennies. Yeah. And so this idea of doubling is exactly what's going on here with this exponential stuff. So we have one person who would take the penny. Other thoughts? Also taking the penny. $100,000. I mean, you can't say no to that, can you? Yeah.
I might just take the 100,000.
Yeah.
Can you imagine counting that?
So, okay, so let's do this real quick. Obviously, this isn't in the notes, but take a look. If you have, we start with 1 penny. That's what you get on the first day, right? Then you times it by 2. On the next day, you get 2 cents. That's the third day. Can you guys just count for me? I'm just going to keep hitting enter. We're counting up to 30. That's the third one. 4, 5, 6. Let's pause right there for 1 second. On the 20th day, you were handed $5,000, which still pales in comparison to Hillary's sure $100,000 check, right? And even if you add, because this is a total, it's not just the 5,000, you get every day. But even if you add them up, you're still probably still around 10 grand. I mean, it's not It's still a lot less than Hillary's 100,000. That was 20, right? Okay, 21, 22. Three digits. On the last day, you got a check for $5.3 million. That goes really nicely with the check you got the previous day for $2.6 million. Yes? Okay, so let's see if we can come up with a way to find this without hitting enter 30 times. But this is surprising, no? 1 penny, doubling every day for just a month. That 1 penny gets up to almost $5.5 million. Yeah. Okay. Yeah, so let's see if we can figure out. So a couple of folks want to talk about formulas here. Some way to do this without hitting enter 30 times. Okay, so here's the basic idea. In this example, why did we have n times 5? What were we doing every year? We were adding 5, right? So repeatedly adding the same number is just multiply. Repeatedly adding 5 is really just 5 times something. But in this case, we're repeatedly doing something else. We're not repeatedly adding. What are we doing? We're repeatedly multiplying. So we're multiplying by 2, and then multiplying that by 2, and we're going to keep multiplying by 2. And if I tell you that, for example, I want to wait for the 7th day, I want to know what happens after 7 days of this. Let's see. I start with my penny, then I multiplied it by 2. That was the 2nd day, and the 3rd day, and then the 4th day. And I repeatedly multiplied by 2, right? And what's repeated multiplication? What is that better known as? As an exponent, as a power. And so if you just typed in 0.01 times 2 to the, let's see, yeah, maybe 7 here. What about on the example that I just gave? 29? How many times did we double? It wasn't 30? Did I? How many times did we double? We started with a penny on the first day. It's 29, right? It's 29 because that first day you just got a penny and then you start doubling the rest of the time. So if I do times 29, let's see if the calculator will give us, I mean, I'm hoping it's that number. Let's see, 0.01 times 2, and then the exponent button is that guy. It's the caret to the 29. That was easier. Okay, so we're already kind of starting to feel the new formula. It's not going to look like a 5 times n. It's going to look like a power. It's not a 5 times. It's going to be a power. So, so I think that we could say something like this. Let's make life a little bit easier and call the first penny P0. I'm going to call 0 the starting amount, and then P1, how much money was given to me on that day? It was 2 cents, and then how much on? Yeah, 0.04. So there's my formula for just listing the first few, like the dollar amounts on those particular days. Let's see if we can come up with some formulas here for PN. First thing I want to do is a recursive thing. How do you figure out how much money you're going to get today based on how much money you got yesterday? You double it. 3 times 2. Did I simulate that on the calculator? That was all those hitting enters. That was times 2, times 2, times 2. What did you have yesterday? Times 2. So that right there is the recursive thing. That's my formula coupled with my starting amount. Together, that's the recursive way. Much better is the explicit way. Pn equals, okay, I feel like I had to take my starting amount. What was it? It was 0.01. And then I had to multiply it by a whole bunch of whats? By a whole bunch of 2's. How many 2's? Yeah, and in our example, it was 29. In general, it's n. Yeah, so it actually is n minus 1 if you start on the first day. I'm going to jog it back so we don't have to play the game with the n minus 1. It's a really good observation. So if we start on the 0 day and you do it 30 times, then you actually have 31 days in the month. We're just going to start at 0 so we don't have to play with that. Okay, so that right there is my explicit formula, and that's the one that I used on the calculator to just zip to the final answer in one shot. Okay, so I think that's fine. And then here's the next thing. Remember we used to talk about the common difference? What was it for the radioactive waste thing? It was 5. The difference between two terms was always 5. Is the difference between these two things always the same number? No. How much did you gain in between the first 2 days? A penny. In the second 2 days? 2 pennies. Between the next 2 days, how many did you gain? 4 pennies. There's no common difference there. Doesn't make sense to talk about the common difference because it's not always the same. But what is the same is what you get when you divide. What do you get when you divide the second number by the first number? You get 2. Let's divide in the other order. Bottom number divided by the top number. How about 0.08 divided by 0.04? 2. How about whatever you had on the 30th day divided by the 29th day? It's 2. So instead of talking about a common difference, we're going to talk about common, what's the word for divide two numbers? Dividend is a good division word, but it's not the right one. That's another division word. Common quotient, that's a good word. There's another word. Quotient is perfectly legitimate. We use ratio to talk about two numbers, but quotient is a good word as well. So we're going to talk about the common ratio. That number right there is the common ratio. Ratio because we're dividing to get it. Okay? And so it's really surprising that a penny could grow to more than that $100,000 sure thing. And in fact, it's not even close, right? It's not even close. And I read some places, an article I read, I don't know, maybe a year ago in Wired magazine, and it was just about, it talked a little bit about exponential growth. That's this, where you keep doubling every year or something like that. And it says that our brains are just not wired to understand exponential growth. We just can't deal with it. We're not good at recognizing doubling every day for a month. We were fine doubling every day for a week. We could handle the small numbers. Do you guys remember after 20 days, how much were we at? It was like $5,000. Like we could maybe buy that. But then there were some reactions that you guys gave when I doubled for the last 10 days of the month. And we went 5,000, 10,000, 20,000, 40,000, 80,000, 160,000, 320,000, and all of a sudden we're in the millions before all is said and done. We're just not equipped to process long-term exponential growth. And this exponential growth comes up pretty often actually when we talk about like global warming and CO2 emissions and all that stuff. And we just had, what was the Nature Day that just passed? Earth Day just passed, right? And so, so I will say, I'll say that the reason that all of this CO2 stuff is scary is because of this doubling idea. We're not good at understanding doubling until it's already gotten huge. And then it's like, whoa, look at that. $5 million on that last day. We're not good at handling doubling in our minds. All we can picture is the short-term doubling when we were at a nickel and a dime and it took a while to get to $1. But it's the long-term doubling that's the scary stuff. And I'm not standing here, I'm not trying to like make a political anything. I'm not denying or affirming any of that stuff with the science and the politics, but I'm just saying the reason that all of those things are scary is because of this idea of exponential growth, doubling every year. Okay, so let's see if we can figure out some general formulas. They're actually written down below. The formula that we had here, let's see. This guy right here was, again, the starting amount. Just call P0 the starting amount of stuff. Why is there a 2 here? What is that called? That's the common ratio. And so I'm kind of thinking that the formula is always going to be, you want to know what the current thing is? You multiply the common ratio by last year's number. That's what you do. And I think we'll see that down below. Here. If you want to know what you have this year, you take last year's number and multiply by the common ratio. Take yesterday's amount, multiply by 2. We buy that formula? Okay, same kind of thing for the bottom formula. Again, let's go back up to this example here. This is what we came up with. We said it was 0.01. How come? That's the starting amount, right? One penny on that first day. Times 2. Why is it 2? Because it doubled every year. That's the common ratio to the end. However many days you get to double, that's how many 2's you need to multiply by. So that formula right there is written in general at the bottom. It's right here. It says you take your starting amount, 0.01, times the common ratio, that was 2 for our doubling problem, raised to the n. However many days you get to do it, 30 in our example. If you feel those formulas, super. If you want to write them down on the reference sheet, super. Okay? So let's see if we can come back up and tackle number 9. Who's our reader now? Alex. Okay, so the rabbit population is going to grow by 20% per year, which, by the way, I think is more realistic than saying you're going to gain 20 rabbits every year. Because gaining 20 rabbits every year doesn't take into account the fact that maybe you have more rabbits, and more rabbits leads to more new rabbits, right? So I think this is pretty reasonable. Okay, we're going to gain 20% per year. So let's write down our starting amount. How many rabbits do we begin with? 1,000. And then we want to know how many rabbits after 1 year. You started with 1,000, you gain 20%. Yeah, and 20% is another 200 rabbits, right? So altogether we'll have 1,200. Let's see if we can find a nice way to write that number instead of taking 20% times 1,000 plus 1,000. Because I'm guessing that's what most of us are thinking. Is you take 20% times the 1,000. That's how many new rabbits you gain. Yeah. Instead of thinking of, so first, is everybody okay with this 20% business? Mary? Okay. So instead of thinking of it that way, let's think about how many rabbits you actually end up with at the end. You started with 100% of whatever you had. Then what percent do you gain? 20%. So how much do you have together when you take your 100% plus another 20%? You have 120%. And so how about instead of doing that addition up there, we just go for 120% of 1,000, which is really 1.20 times 1,000. What is that? That's 1,200. I mean, it's been 1,200 the whole time. But I guess all I'm saying is that I'd like to figure out the 1,200 by multiplying by 1.2. And so then in the next year, you take whatever you had. How many rabbits did we have? 1,200. And what's our multiplier? 1.2. Every year, 120% of what you had the year before. Madonna? Yes, then we're going to use exponents as well. That's a good observation. That's not right. 1440 is this one. Okay, can you guys use that same idea to find the next number? So we take the old population of 1440, multiply it by the 1.2, 17, how much? 28. Jocelyn. Okay, Jocelyn says this. I think Wadada was saying something, was feeling something similar. Can we try that formula and then we'll see if we could figure it out? Let's first see if it works. Let's go ahead and plug in 3. I know I already have the answer for 3, so this will be a good way to decide if we did it right. So we do 1,000 times 1.2 to what power? To the third. So folks with calculators, type that in. Let's see what we get. We get 1728. Okay, so I like that formula. In fact, I like it better than what we did over there in blue. What we were doing here in blue was this recursive idea. To figure out what you have next year, you use the current year's number and multiply by 1.2. Enter, 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 enter. But Jocelyn's got this explicit formula he wants to use. It's 1,000 times 1.2 to whatever power, and then you just jump to the answer. You jump to the answer for the third year instead of having to first find the first 2 years. Right? So that's a really, really nice formula to use. This guy right here is the explicit formula. We haven't quite written the recursive yet, but we will. But first, I want to see if you guys buy that explicit one is something, whoops, something that you could have written down based on this formula that's out here. It says Pn equals, what's the starting amount of rabbits? 1,000. That's there. Times the common ratio. What did you have to multiply by every year? It wasn't just 20%, it was 120%, 1.2. That was the number we kept multiplying by. So in the parentheses goes 1.2. Up there in the power, always n. Always how many years you're waiting down the future. That's Jocelyn's formula. Okay, far less useful, but we'll write it anyway, is the recursive version of things. Again, it starts with the starting amount. What was the starting amount of rabbits? 1,000. And then we need a formula. The formula is supposed to do something to the number of rabbits you had last year, 1 year ago. How do we find this year if we know last year? Times it by 1.2. Isn't that what we did over and over again? We just kept taking last year and multiplying by 1.2. I realize that I'm asking you guys to make a leap here, and the leap is somehow that this n has something to do with this n minus 1. I haven't been saying n and n minus 1. I keep saying this year and last year. That's the leap I need you guys to make. Pn is a generic this year. If n is this year, then what's n minus 1? Last year. Okay. So to find the population this year, you take last year's population, multiply it by 1.2. And I'd really like for you guys to see that that's the same as this other formula here. Tn equals Pn minus 1 always times the common ratio. What was the common ratio? 1.2. Questions on that? Okay. I want to make up a new problem. And you should know that I am making up this new problem thinking about the third exam that I'm going to give you in a few weeks. So pay attention to this problem. Okay, suppose that that I have the first 2 years of information about some population, something. Let's say that the first number is going to be 15. Scratch that, 16. First number is 16. And then the second number is 24. Can you tell me what the third, what the next number in this list is going to be? Talk to your neighbors. Find the next number in the list. P2 is 32. Agree? That's the next number? What did you guys say?
Could also be 36.
36. We have 2 different possibilities here. 40? How'd you get 40? Could the rule be add the 2 previous numbers like we did with Fibonacci? It could be anything. I asked you a question that you could answer anything you want. Easiest question I ever asked. P3, P2 could be cat. I mean, it could be anything. Like there's no, I have to give you more. I can't just tell you 2 numbers and say find the next one. I have to give you a rule. So one possibility is that here are the two numbers and it's linear. Another possibility is here are the two numbers and it's exponential. Blake's example, here are the two numbers and it's a Fibonacci thing. We're not going to do the Fibonacci today, but it's a really, really good thing to point out. Could be anything. It's a good pattern at adding the previous two. Okay, now that we're saying that there's two different possibilities, let me ask you guys, first focus on linear. See if you can write down recursive formula and explicit formula for linear and use either of those formulas to find P10. So assume it's linear, write down recursive formulas, explicit formulas, and then find P10. So here in purple, I've got my recursive formula. The recursive formula is up above. It just says, I'll show it to you again, but it's up above. Recursive formula for linear is right here. It says Pn equals Pn minus 1 plus the common difference. That is always the recursive formula for linear things. So there it is. Pn equals Pn minus 1 plus common difference. Every time it's up by 8, because that's the only two numbers I gave you, and it was up by 8. Okay? Assuming it's up by 8 every time, what's the next number? 32. That's where the 32 came from. That's where most of you guys went. In fact, remember I had said our brains just aren't really wired to deal with exponential. I gave you two numbers. Almost everybody in the room said, oh, every time we gain by 8. That's a linear thing. But very few people thought about it as a multiplying 16 by something to get 24. We'll do that in a second. Here is the explicit version of things. Again, the formula is up above, but it says Pn equals start amount plus common difference times n. That's the formula. And then if you want to find P10, would you rather do the recursive or the explicit? Explicit. Much, much better if we have it. Instead of n's, what are we putting? We're putting 10 for both of those n's. So this becomes 16 plus 8 times 10. 16 plus 8 times 10 is 96. That's what happens 10 years from now, 96 somethings. That is everything there is to know about those two numbers and linear growth. What do you think we're about to ask? It's about exponential growth. Okay, linear we're really good at. What did you have to add to 16 to get to 24? 8, no problem. Exponential, we're not as good at. Question is, what do you have to multiply 16 by to get 24? It's not as simple. Yeah, it's not as simple as doubling like we had before. If I just give you numbers and they're always doubled, you probably find that pattern. But here, 16 times something to get 24, maybe it's not so clear, but what you could always do if you're doing an exponential thing, I'll just write down my two numbers again, 16 and 24. But if you want to find that common ratio, it is always the next number over the previous number. 24 over 16. The next number over the previous number. In that order every time. And here we get 1.5. That's what you have to multiply 16 by to get 24. So if I give you two numbers, you need to find this ratio. The second one divided by the first one. Always in that order. So what are we saying? Well, now we're saying that every time, you're not adding 8. What are we saying you do every time in this sequence? Multiply by 1.5. That's this rule. Okay, same questions as before. Assuming now that we're doing this exponential thing, can you write recursive formulas? Can you write explicit formulas? And can you find what's happening in the 10th year? Go ahead. So again, starting with 16 and 24, what's the common ratio now? 1.5. Every time we multiply by 1.5. So we have a recursive version of things. Pn equals Pn minus 1 times the ratio, times 1.5. That's it. We have an explicit version of things. Pn equals the starting amount of 16 times the ratio of 1.5 to the n. That's the explicit formula. And then finally, if you wanted to plug in n equals 10, go to your explicit formula and do it. So we get 16 times 1.5 to the 10. And you can type that in and get something around 922. Oh. So, okay, so then I'll say 923. On the test, I'll be very clear about where I want you to round it. So around 923 is good. And yeah, I mean, you can see the difference between linear and exponential. What did we have after 10 years? Let's say these are rabbits. We had 96 rabbits if it kept growing by the same amount every year. But if it keeps multiplying by the same amount every year, we have 923. Big, big difference. Okay, any questions on using the formulas? Okay, so we're going to skip 11 and we're going to skip 12 and ask you guys to try this group activity here. Starts there with the middle of this page. I'll walk around for questions.